Welcome to my presentation on claims frequency modeling with deep learning, this time the long version, 15 minutes. So what is claims frequency modeling? It's one of the key aspects that any insurance industry, any insurance company has to do, and they have to understand this very well. It's a major part of the business. The reason being that the price of an insurance policy is usually determined by the expected loss that a policy makes. And the expected loss consists of two components, namely how often a claim occurs, which is the claim's frequency, and how expensive a given claim is, which is the claim severity. So basically what we do in this project is one part of pricing an insurance policy. It's also used for risk selection furthermore, and together with pricing and understanding the expected loss, it also determines the capital requirements that an insurance company has. Any insurance company needs to provide a certain amount of capital to make sure that they actually can pay the claims that arise. The traditional approach was to use Poisson regression with generalized linear models, but there's nothing that prevents us from using machine learning or deep learning. It's all just about optimizing the log likelihood, which is just the standard loss function that can be optimized using any machine learning technology. The technology I used was first of all Keras, but it turned out that Keras is not good for the job that we're doing here, mainly because of the third variable that comes into place, which I did not talk about so far, which is the exposure. Because of that, I had to go back to a lower level API, which was TensorFlow, but the layers API was enough to make everything work. I did everything from an R and RStudio server launched on AWS. I'm going to go a bit into the particular AMI that I used. I also did a comparative model using GBM's gradient boosting machine using H2O. So let me briefly talk about the data. It's about a French third-party motor liability data set. So third-party motor liability means that if you have an accident and you injure a third person, then the insurance company pays for the injuries of this third person. The dataset is available, it's an open source dataset, and it's available from the CAS datasets package, which is available on the website listed here. And if you ever need datasets for insurance, then it's always worthwhile to look into this package. It comes from the computational actuarial science with R. The dataset at hand has around 700 policies and 10 variables. So from that point of view, it seems to be a rather big dataset, and it could be beneficial to use machine learning rather than GLM. The target variable in a sense is very skewed, which is normal for Poisson regression, but still 95% of policies have no claim, and 5% have one claim, and more than one claim is very, very rare. As explanatory variables, just to get a feel, we have bonus malus, which is usually the most important. It tells us about the previous history of a person. Age, which is driver age, and vehicle age. With the vehicle brand, we have gas, we have a few geographical things. And then we have the exposure, which is a very important variable, and it tells us how long an insurance policy has been in place. And it's important because you cannot do just ordinary Poisson regression, because it's of course very different whether a policy that's been in place for a full year had no claim, or whether a policy that's in place for 1 day had no claim. And this is measured by the exposure variable. And this is why the reason why we can't simply use the Keras package. Let me talk about a bit about the setup. I did everything on Amazon AWS. I launched a P2 machine, namely a P2X large machine on AWS, using a very good RStudio AMI. I've actually detailed on this slide the setup. And there's this RStudio AMI. It's RStudio server Amazon machine image. And basically what you do is you go to your EC2 here, and then you just launch an instance. And when you launch an instance, you basically just go to the community AMI, and then you search in your region for this AMI that's given here for this ID. You paste it in and launch an EC2 instance as usual. And the good thing is once you do that, you have your running RStudio server together with CUDA. It has TensorFlow installed. It has all of the Markov chain Monte Carlo samplers, JAG, STAN installed. So it's more or less a full-fledged statistics machine that you have with very few clicks, and it can be a very fast one if you use GPU instances. And so that's what I did. And in the end, all you have to do is you just have to copy paste the web address of your AMI and end it with the port 8787, and that's it. And you're up and ready to do your analysis. All right. So now let me go a bit into why Keras actually does not do this. So let me show you a bit about the dataset first, and then go into why Keras does not really work out. So here we really see the dataset. We have here the claim numbers, and then we have this exposure variable, which tells us how long a policy has been in place. Then we have also the power, we have the age, we have the driver's age, the brand, the bonus malus. We have these geographical factors, and we have whether it's gas or not. All of those are a bit more explained here. So why is the exposure variable so important? So why can't we just use least squares regression? It's because of these extreme cases. If we just modeled the claims frequency as, say, the number of claims per exposure, we'd have to somehow weight it. But there's an alternative, and that's actually statistically correct. Rather than just modeling the number of claims, what we see on the left-hand side here, or the log of the number of claims, so f of x is the function that we want to learn, we just want to learn the log of e of x, and we just add the exposure on the right-hand side. So we're just learning still the number of claims, but we are sort of dividing it by the exposure. And still doing Poisson regression though. And this leads to the following log likelihood that we want to maximize, where yi is the number of claims, log of f of xi is our target function, or the logarithm thereof, si is the exposure, and f is again the target function. What I then did was the standards of machine learning. So here in this code snippet, we see that I defined the train indices, so a sample from my data set around 90%, without replacement, and then I define the training set as the slice of my data frame that come within this training set, and the test is exactly minus this training set. So we take out everything that's not in the training set. And for later use, as I said, I used H2O to compare it with standard machine learning models rather than deep learning models. I also uploaded to the H2O server. Then we can see here the plots for exploratory analysis and also the count. You can count explicitly how many claims have how many policies have how many claims. And we see really the major part is 0, 1 claim. 2 appears a few times, and everything above 4 seems to be a data problem. It's very rare that a policy could really have 11 claims. Here you see the code for a baseline GLM model. So of course it makes sense if you do deep learning, you have to compare it against something useful, and that's not totally trivial to understand how much benefit you actually get by using deep learning. And that's what was done here by using the baseline model. And here you see the code for training the baseline model, and here you see the code for evaluating the deviance. So the training deviance is this 31.9, and the test deviance is this 32.9. Here you see the code snippet for preparing the data for using Keras. And so what I did is I used this recipes package, which is a relatively new package by RStudio that sort of allows you to work in a tidy workflow to do all the data pre-processing. You just say, you still state a formula, you give the formula that you want to train, and then you can do with very nice piping through, you can do a centering, you can scale, you can introduce dummy variables, and then you just sort of bake this thing. You use this object that you created here to bake new data sets. And that's what I'm doing here. So I'm getting the training explanatory, the training claim numbers, and the training exposure here. Now theoretically we could still work with Keras, because Keras allows us to actually define custom loss functions, as we can see here. A custom loss function just takes 2 arguments, namely the true predictions and the predicted predictions. And you could still use Keras theoretically by just saying, well, my true y's, this is not a tensor that only has one dimension, but that rather has two columns. And one of these columns is the counts, which I'm saying here, and the other is the exposure. And then I could still return the loss function as required. But what I show in the next code snippet is that this actually does not work. You can train it, and then you can check it against the baseline GLM, and you see that you just get different components. You just get different coefficients, and so you also get different predictions, get different deviants, and your Keras model is just not right. There's various things that I tried to rectify this situation. For example, as you can see, the loss function here actually splits quite nicely into two components. One that just depends on the predictions and the exposure, and the other that just depends on the counts. So in a sense, you could split this into two components and have two outputs, and that's what I did here. So you basically have two outputs, which is once the activations, which are the log of the predictions, or if you think about classification, this would be things like the logits, and the true predictions. And the input is the x input, and your loss function then is sort of has an exposure loss and a count loss, which are exactly the two pieces that appear in this loss function up here. So you could think that this works, but again, if you train the model, it just does not really work out, and the model optimization is sort of problematic. So in the end, this was the reason for me to resort back to TensorFlow. The first step that I took was actually to make sure that everything I do in TensorFlow adds up to be correct. So the first step for me was to do just to reproduce a GLM model that I could fit with standard R, and just be sure that I'm actually having my loss function correct, my target function correct, my activations correct, so that I really can then with confidence go into deep learning. So this situation is very easy. We just have an input tensor, which is I have the predictor variables, I have my counts, and I have my exposure. And then all I'm doing is I take a single dense layer where I feed in my inputs, and then I take the exponential, because with Poisson regression you need to exponentiate your activations to get the counts. And then the loss function is just what I had before. It's just the counts times log of predictions minus predictions times exposure. Then I'm defining an optimizer, and that's it. And then here I have the training code. I'm just optimizing over 400 epochs, as you can see here, and I'm just running the optimizer 400 times. And if the epoch is 0 modulo 50, so if it's a multiple of 50, then I'm printing intermediate stats, as you can see here. And I'm also and then I also return the final weights. I don't do that later on because I don't care about them anymore, because I'm sure that I'm fitting correctly, and I return the final predictions. And just this comparison, you can see that the predictions on the x-axis, you see the predictions that's by R's GLM function, and on the y-axis you see the TensorFlow predictions, and you see that they match perfectly. And similarly, you see here the coefficients. They don't match up exact perfectly, but that's almost correct. And I think that if I train for more than 400 epochs, they will match up perfectly. So now that I'm sure that I've actually done everything correctly, I go into optimizing the network. And for optimizing the network, I split my training set further into a validation step and a training set. And the validation set is not shown in the code here, but I played around a lot with the coefficients, with the number of units, with the dropout and things like that, so that I get good results. And good results means good results on this validation set here. So the first step was to just go with a single hidden layer. So all I did was I introduced the new hidden layer here that gets as input x. And the only other change that you need to do is to give the output layer the input of the hidden layer. And everything else is the same. And then I train this over 1000 epochs, but this time I print the training loss and the cross-validation loss. And I also return the test predictions. Because in the end, I don't use the test set for anything more than computing deviance. I don't use it for model selection, but I return the test prediction and then immediately compute the test deviance. And in that case, it's 0.3218, which is quite a bit better than the GLM. And then I go further, the same thing again with 2 hidden layers. And the train function is exactly the same, with the only difference that here I have an additional dropout layer. And I have a dropout layer where, again, the rate was tuned using a validation set. And the dropout layer needs an additional tensor as input, which is the train flag, which is just a boolean that's now also passed via the train function. That's the only change in the train function, that it actually passes through. When we're optimizing, it passes the training flag to be true, and when it's evaluating the loss, it's passing the training flag to be false. I'm training again for 1000 epochs, and that's, as it turns out, is enough. And I'm compute the testing deviance. We'll see the results later. Here I'm doing more or less the same thing, but I'm going 3 layers deep, and then I'm going again even deeper with 4 layers deep. What's also very interesting is that you can actually do plots to understand how your output depends on your input. So here I'm, for example, plotting the marginal results. So I'm plotting as input variable the bonus-malus variable, and I'm plotting as output the fitted results of my deep neural network. And it's sort of what you would expect. The people that have a high bonus-malus score, which means that they have a high malus score, they tend to have way more claims. Of course, here in the very right, there are very few people, and so the model gets very uncertain. But you sort of see this linear trend here in the beginning. And as it turns out, this actually tends to be the most important variable. So now you could go about trying to understand your model by looking at such dependency plots. I then also went 4 layers deep. There's nothing new in the code here, and as it turns out, 4 layers does not give any additional benefit. I also used H2O, as I explained in the beginning, to train a competitive model to compare. And what I did is I used the H2O.gbm function, which trains a gradient boosting machine, to train a Poisson model, which you can see here. It's specified by distribution equals Poisson, and you can set an offset column, which I'm setting here. And then I'm computing the deviance using this H2O model. So interestingly, what you can see is here the full comparison. We can see that the GLM does not perform so much better than a null model. A single neural network with a single hidden layer performs roughly the same as a gradient boosting machine, and actually going deep pays off in that case. A neural network with 3 hidden layers performs quite a bit better than a neural network with 1 hidden layer, and slightly better than a neural network with 2 hidden layers. Now, of course, this is not ready to use as is. There's a lot to be done if you want to deploy such a model in practice, and this is the caveat that I want to spill out. This is just a very proof of concept thing that was done here. This is not ready to be deployed in any way. Namely, what's missing, for example, is the impact analysis. Well, as I said, you have to do claims frequency model and claims severity modeling, and you have to understand how this model impacts the final prices compared to a GLM. And what's very related is the stability analysis. Deep learning often tends to overfit in a sense that you can't really see just using a training validation approach. So what does the model do if it just changes some input parameter slightly? Is it stable in that respect? And it sort of has to be from an insurance point of view. You need to understand the model quite a bit, so you need to open the black box. For example, in France, you're not allowed to use gender as a qualifying variable, and you're actually not even allowed to use proxies of gender as a qualifying variable. So in a sense, as a modeler, you need to be able to prove that your model is not discriminating against gender. So understanding, actually opening up this black box is very, very important, just for regulatory reasons. And finally, the claim severity part is totally missing, so it's not ready to be used for pricing. But still, these are the major conclusions. One of the also major conclusions is that if you use the right AMI, you have very minimal setup, and that's what's happening a lot. So thank you